Okay, YouTube, in our last video, we looked at the graphs of simple rational functions, and we say that a rational function, just to kind of refresh our memories, is any function of this form f of x where we have a polynomial over another polynomial. And by the way, our q of x polynomial can't divide by 0. So what we were looking at specifically were functions of the form a over x, and in particular we had looked at the function 1 over x. And so what we're going to do in this video is we're going to extend this to include all transformations of what we call the parent function. So with our transformations, the neat thing about transformations is that we've seen these before, and as a matter of fact, as I list this here, a over x minus h, we'll put this in, say, parentheses here, plus k, this would be our transformation of the parent function. And so in terms of what we would see changing here, we would say that these changes would occur in correlation with a, h, and k. And so looking at this, I suppose we would say that what we want to really know is our parent function 1 over x first, and then go from there. So let's remember about 1 over x if we're going to draw f of x here. It has an asymptote at the y equals 0 line, or on the x-axis, and it has an asymptote on the y-axis at x equals 0 line. Also, we were to say make a table of values. We say plug in 1, we would say we'd be at a height of 1. Plug in negative 1, we'd be at a height of negative 1, because we're taking 1 over x, and 1 divided by 1 is 1. And of course, 1 divided by anything, we could say like 1 divided by 2 is a half. 1 divided by 3 is a third. Here we got this parent function that looked like this, you guys. And so we would say, let's see, negative 2, negative a half, negative 3, negative a third. It just keeps getting close to this asymptote. With this function right here, what we could see is that it's kind of centered upon 0, 0. Centered upon 0, 0. But what I want to do is I want to make kind of a drastic statement here. As we look up in this here where it says to graph a function of the form y equals a over x minus h plus k, what we're going to see is that it says that our asymptotes are at x equals h and y equals k. But what I want to do is I kind of want to justify this here, because our h value, let's recall some things here. H is horizontal shift. Horizontal shift. And with respect to horizontal shift, it's a liar. It's not honest with us here. That is to say, whatever h looks like, it's going to be kind of the opposite of that because of this difference relationship we see here. Then we say k is vertical shift. Well, what I want to do is suggest something here. Not that it's honest, but we're going to write that there. But that if we were to shift this graph of the parent function here anywhere left and right, then our y value would be directly affected by whatever the vertical shift was. And so we would suggest that our y equals asymptotes, or our horizontal asymptote, is always going to be at the height of k. And also, because we started at 0, 0, and we shift left or right h units, then we're going to shift left or right h units from 0, which puts us at an x value of exactly h. And so in general, we're going to say that any graph that's in this form right here, we're going to identify a, h, and k, but we could say that the h value directly affects where the vertical asymptote would be, and the k value would directly affect where the horizontal asymptote would be. We would say, generally speaking, we could kind of say, quote unquote, it's centered at hk. So we'll kind of look at it this way, quote unquote, centered at. We'll say that this is where our two asymptotes would intersect, and then from there, using our a value, we could plot some points to the left and right of these vertical asymptotes here. And so in terms of sketching these, we're going to draw in our asymptotes and then plot some points to the left and right of every vertical asymptote. And this is an important step here. Remember that our graph is interesting in the middle. Everywhere there's a vertical asymptote, we're going to see some interesting parts of our graph. Everywhere out on the edges is going to approach this asymptote. And so we'll only plug in, and as you notice here, 2 to 3 x values to the left and 2 to 3 x values to the right of every vertical asymptote here. So let's take a look at an example of where this might occur here. We say that the graph of g of x here is negative 4 over x plus 2, that minus 1. So the first thing I want to do is I want to identify some things here. We say a, h, and k. And in terms of a, h, and k, it looks like the a value here is a negative 4. And we say h, it's backwards, would be a negative 2, and our k value looks like negative 1. So let's go ahead and describe our transformations here. We're going to see that we have a reflection, reflection over the x-axis by making our a value negative here. Also, we could say a vertical stretch by a factor of 4. In terms of our translation transformations, we can say that it's going to shift and it appears it's going to shift left 2 units. And in terms of vertical shift here, we can see that we have shift down 1 unit. And so to sketch this graph here, let's go ahead and start with our asymptotes. We could say that the asymptotes, we're supposed to list these here, so let's go ahead and do this. The asymptotes, we would say that our vertical asymptote would shift left 2 units from where it initially was. So we could say that our vertical asymptote is going to be at x equals h, or in this case, x equals -2. So we would say this is now at x equals -2, and because our horizontal asymptote, typically on the parent function, is at the x-axis, but we're shifting down 1, we say that our new horizontal asymptote is going to lie right here. And so in terms of putting this graph together, this was kind of the first step we want to get out of the way, and I don't mean to imply that we put a dot there, but that would be centered at this point here, and this point here is -2, -1. You can see that it's because we shifted left 2 and down 1. Now, for step 2, it says plot points to the left and right of the vertical asymptote. So what that means is, yes, we actually get to make a table of values. And in terms of what you're going to put into this table, it's always the case that I would prefer to have 2 points to the left of and 2 points to the right of every vertical asymptote. So we're going to go with -4 and -3, but we're also going to go with -1 and 0. And just because I love plugging in 0, we'll start with that. If we were to plug 0 into our function, let's go ahead and take a look at this. Our function g of x, our rule, is -4 over x plus 2 plus 2. And I'll do this also, plus 2 minus 1. And so when we plug these in, we say start with 0. We're going to get, let's see here, I suppose we would get a -4 over a positive 2 minus 1. So we end up with -2 minus 1 here. We get -3. And so -3, we got that when we plugged in 0 here. So we'll put that right there. Let's now, how about instead of plugging in 0, and you know what, I'm going to take this out, all this here. Sorry. I just want to get that 0 out of there. We got a -3 here. So if we plug in a -1, I just want to show you here, -1, here we would get down here, I suppose, a positive 1. And so getting that out of the way, we say -4 over a positive 1 minus 1. We get a -4 really minus 1 here. So -5 is the value we're going to get here. So with -5, I say -5. Let's go ahead and take a look at plugging in a -3. Now -3, what happens now is we get a -3 plus 2, which is a -1. We actually get a -4 over a -1 this time, which gives us a positive 4 minus this 1 here. So 4 minus 1, I suppose we get 3. So let's throw this up here, 3. And as we plug in -4, I can keep that there now, since it's the last one we're going to plug in. We basically get a -4 or -4 plus 2, which is -2 minus 1, which gives us a 2 minus 1, which gives us a 1. So all we're going to do now is we're just going to go through all these points on our graph. We say left 4, up 1. We say 1, 2, 3, 4, up 1. Here's a point on one of our branches. Left 3, okay, up 3. So we go 1, 2, 3, 1, 2, 3, okay. Now from the origin, we'll go left 1, up 5. So we say from 0, 0, we'll go left 1, 1, 2, 3, 4, 5. Oh, sorry, down 5. Left 1, 1, 2, 3, 4, 5. That makes much more sense. And then here we say 0, -3. So this is our y-intercept of our graph, 1, 2, 3, right there. So to graph this, we're just going to use our basic knowledge of the shape of this graph and say, hey, look, you know, what we get here is something that looks like this. So because we labeled our points in the table, we don't need to label them on the graph. But you do need to have a table of values. We also should always label our asymptotes. So we say y equals k, or y equals -1, and x equals h here, or x equals -2. And the last thing we always want to do is describe the domain and range. And so with respect to rational functions, we can get used to saying this a lot of the time, all real x except, and we say all real y except. So we're going to get this all real x values such that x in this case, it was not allowed to equal -2, because if we put in a -2 right here, our function is undefined, okay? And as we look at this range of values, we say all real y values except, well, all real y values except for the one where we have an asymptote. We say y equals -1. So we say y cannot be equal to -1. So I want you to try this on your own with the problem I've given you on your sheet there and see what you come up with. Remember to describe domain and range. Remember to label the asymptotes and make a table of values. Cheers.